Going on, party people? It's your favorite chemist from Western PA here, Donnie Trong, and I'm here to talk about bomb calorimetry and how we're able to find the resonance energy of benzene using Cygress, and which is a theoretical method and also experimental methods. So first, we're going to talk about some of the compounds of interest. So benzene, this has three double bonds, three CH bonds, and three CC bonds. Cyclohexene has six CC bonds, 12 CH bonds. And CDDT has 12 CC bonds and 18 CH bonds. And so this is an isodesmic reaction. So basically, what was originally thought was that you can add these bonds together of benzene and cyclohexene, and that would equal the amount of bonds present in CDDT. And so they originally thought that also you can just add up the heat of combustion for benzene and cyclohexane, and you'll get the heat of combustion of CDDT. And that is questionable only because it didn't take into account of resonance. So resonance is just this idea of electrons being able to delocalize in the p orbitals of the benzene molecule, and it has three pi bonds around it. And so this is more of a stability, and it creates this extra stability and is a factor that we have to take into account when we look at the heat of combustions. And so using that, we're actually able to use Hess's law and the cycle associated with it to find the resonance energy of benzene. And so the first three require literature values, and then D, E, and F, those are what we find experimentally. And we're able to do this because it's a state function, and so requires thermodynamics. And so Hess's law is a great way to find the resonance energy of benzene. And so let's talk about bomb calorimetry here. And so bomb calorimetry is a good way for us to find the heat of combustion for the liquid phase of CDDT and cyclohexene. And we actually are not able to do that for benzene for safety issues. And what was looked at prior was like trying to figure out the heat of combustion in the gas phase, but that doesn't generate accurate results. So bomb calorimetry is used. And so we came up with some hypotheses. And so basically, the first one was that CDDT will have a higher heat of combustion compared to cyclohexene, and that's because it has more double bonds and is larger. And so the amount of pi bonds that are getting broken will result in more energy being released. And the second hypothesis is just when looking at the theoretical and experimental methods, so methods of Cygress will actually generate a lower resonance energy, and that's because it takes the lowest conformations of the molecules, or the lowest energy conformations of the molecules CDT and cyclohexene, while the experimental takes on various conformations and they will have a higher enthalpy, hence higher energy. And so when looking at this picture here, it just shows the materials that we're using. Most importantly, the gelatin capsules that were required for the cyclohexane samples. Um, Next up kind of shows what we did. So we measured an ignition wire and we connected it to the bucket here with the sample in the bucket, and we're able to load that into the calorimeter as shown here. And we are able to connect the temperature probe as well as a stir. The temperature probe helps us find the temperatures at various times. Then we add like around 2 liters of water. We pressurize, and then we pressurize the bomb, and it is ready to go. And this is how the kind of the setup that shows it. And kind of this red button here was kind of just the ignition button. And once we let it stir for about 2 to 3 minutes, we kind of hold this button in, and all you hear is a loud bang. No, I'm just kidding. That's not what you see or hear. So after the experiment, we're actually able to generate these temperature versus time graphs, which give us all these parameters here. And these are very important for finding the change in temperature for each of the samples. Shown here are kind of what each variable represents. And again, we're able to find these in Excel with our graphs being plotted. Shown here is the equation that we actually use to find the change in temperature. And again, shown are what each variable represents. And so here's kind of like an example of what would happen when we do this calculation for the CDDT run one. We find a change in temperature 5.849 degrees Celsius. And this slide shows all the results for each of the samples, right? And so the top ones are the CDDT and the bottom ones are the cyclohexene. And like I said, from these graphs, we're able to determine these values shown here. This is the mass obtained experimentally, and these are the results. And we can use that for the following calculation, which is the total heat. So the first equation is kind of just the general form, right? It looks at the calorimeter heat capacity of the bomb, and then also the change of temperature. And then the second one is more of a correction factor. This requires the ignition wire and the heat of the ignition wire and the heat of the unburned wire, and also the gelatin capsule, right? So for cyclohexane, for example, we have to subtract out the heat of combustion for the gelatin sample, and that helps us find the internal energy of combustion. So we're able to relate this to, but for more exactly, when you divide the internal energy of combustion by the moles of the sample, then we're able to find the heat of the sample. And this is important in order to find enthalpy of combustion for both CDDT and cyclohexane. And so we use this equation shown here. And we're able to find the enthalpy of both. And this change in N of gas is just the number of moles, or the change of moles of gas, and it's negative 4.5 for CDDT and negative 3 for cyclohexane. And then we use the gas constant R, and then T is equal to 298 Kelvin. And using that equation, we're actually able to find the enthalpy of combustion for CDDT and cyclohexane. And here it kind of shows our results. And this kind of proves our first hypothesis, or supports it, sorry, as the CDDT enthalpy of combustion is way higher, more than twice the heat of combustion of cyclohexane. And then we finally are able to find the enthalpy of vaporization of CDDT using the integrated form of the Clausius-Clapeyron equation, and then the values that were given in the lab manual. And so this is very analogous to y is equals to mx plus b. So we're able to plot these values using natural log of p of pressure over 1 over t, and we're able to find a slope, right? And since it's analogous to y is equals to mx plus b, all we do is we multiply the slope value by the gas constant R and times 0.001 to get our value in kilojoules per mole to keep the units consistent. And it's negative 47.675. And then the literature values were obtained through NIST, and these were the values that we were able to find. And again, this kind of shows our results of all the required numbers that we're able to achieve to find the resonance energy of benzene. And the bottom here, again, shows each what each value and what step it correlates to. And we're able to get a value of 221.104 plus or minus 76.874 kilojoules per mole for the resonance energy of benzene. And then we're able to do Cygress. And using Cygress, we're actually able to find the heat information for benzene, cyclohexane, and CDDT. And using this balance equation down here, we're actually able to just do products minus reactants, and we're able to get a resonance energy of 152.12 kilojoules per mole, which is lower than the experimental, which was which does support our hypothesis. And there's a 45.35% error. Like I said, for the discussion, at least, both our hypotheses were supported, and the error was large. And let's talk about that. So what happened and what can we do? So clearly there are slight issues with the experimental method, and Cygress was the better method. But why? We only did 2 trials, so we can try to add more trials into the experiment for CDDT and also cyclohexane, sorry. Time limited though, so yeah, I would say more trials would generate better and more consistent results. And we actually weren't able to get a good determination / accurate determination of the change of temperature, because the temperature probe, there'd be times where there'd be fluctuation, does not give us proper temperature values. And so this can be harmful for our results. And then finally, we could talk about how the heat of both the cyclohexane and CDDT, how that would have been leaked in the bomb jacket or the calorimeter itself, but we weren't able to track that, right? So there's no way to tracking that. So maybe we could find a better way to track the heat that is getting lost. So is there more than one method? Let's find out. So if you look at cyclooctatetraene here, and we see that it has an extra double bond compared to compared to benzene. Benzene has 4, 3, this has 4. And so what we could do is find the heat of combustion of this double bond here and subtract it from the heat of combustion of cyclooctatetraene, and then we were able to find the necessary value for the resonance energy. But what about bond enthalpy? And we can just scratch that off the list because bond enthalpy doesn't take into account resonance, and we actually care about resonance in this lab report. And so, yeah, that is not a valid method. But what about the heat of hydrogenation of cyclohexene? So this we have to consider hydrogenating the double bond across the cyclohexene, and then we multiply that value by 3, and then we take this value and subtract it from the heat of hydrogenation of benzene, and this actually does give us an estimate of what the resonance energy of benzene could be. So yeah, those are 2 out of the 3 methods that we can use. And let's talk about some resonance. So why this trend happens and why benzene has the highest resonance is because it doesn't experience ring strain like cyclooctatetraene. It's aromatic. It follows the Huckel rule of 4n plus 2. And the cyclic molecules in general experience better delocalization compared to its linear counterparts. So here's kind of why the trend is why it is what it is, and why benzene has more resonance energy. All right, thank you. Hope you learned a lot. See ya.